Can you see it?
Yeah, looks good. Let me hit record.
Okay.
Okay, our next speaker is Stefano Andriolo from KU Leuven, who will be telling us about duality and the axionic weak gravity conjecture. Take it away.
Yes, thank you very much. And can you actually hear something? Because there's my neighbor making some noise working outside, so I hope it doesn't bother anyone. In case, let me know.
Can't
And
so far.
so, yeah, can you know? It's okay?
Yeah, sounds good so far.
Okay, great. Thank you, Colin. Thank you, John, for putting this amazing seminar series together and inviting me today. And so I'm going to talk about our recent work with Jimmy, Hiroshi, Gary, and Toshifumi. And this is the paper. Let me see. Okay. So it's a talk about the weak gravity conjecture in its axionic version. So this is like a swampland talk. So quickly, let me review. I cannot find the pointer. So we know that not every effective field theory can be is consistent can be consistently completed in quantum gravity, and we have this notion of which effective field theory can be completed and which effective field theory cannot be completed. So the former ones are termed to be in the landscape, and the second one in the swampland. And the whole point is to try to identify this criteria, defining the boundary between the swampland landscape. So in the recent years, since 2006, when the swampland program was started, there have been a lot of conjecture criteria to define this boundary. And I really like these pictures, this interpretation by Hiroshi's, that puts like all these conjectures in a in a really nice diagram where it plots rigor against like usefulness. And yes, we can see it. I found it pretty interesting. And today I will talk about the weak gravity conjecture. And it's really interesting that this Weber conjecture that all these conjectures are related, and there may be this is a hint towards something deeper, which we can call the string length principle, that that states that maybe all consistent quantum gravity theories are all part of the string landscape. So let me give some motivation for our work. And first is to test these swampland criteria. So there have been, so how can you do it? So either you test their self-consistency, trying to check how they are linked together in their relationships, or you check the consistencies of this swampland criteria and conjecture with other principles like unitarity, causality, locality, analyticity. There are a lot, and yes, basically all these principles define how rich your quantum gravity theory is or is supposed to be. And also, in so doing, we want to highlight and find all the relevant properties that quantum gravity has to satisfy. And in so doing, the main point is understand what makes string theory so special. And maybe we can also answer the question, is quantum gravity really unique and given by string theory? Because many times you can see, so string theory is so rich and maybe too complete, in a sense that it's too nice to be, yeah, it's really nice and rich, and like an insurance with full options if you want. But many times you want just to understand what quantum gravity really is, and yeah, we want to understand which of these properties are the relevant ones. And today I will focus on this, so studying the testing, the consistent with other principle, namely I will focus on positivity conditions, and which comes from unitarity, causality, and locality of scattering amplitudes. So if you have to take away something from this talk, is the following punchline. So we analyze the weak gravity conjecture in its axionic version against positivity conditions, as I just said, and the result is that in some system, I will tell you about, let's say, simple systems, positivity is sufficient to imply the weak gravity conjecture, but more often this is not the case. So positivity alone is not enough, but specifying some other ultraviolet information that the theory, the effective theory, has to obey can be sufficient to satisfy the weak gravity conjecture. We do it with imposing a SL2R symmetry, but we don't exclude, actually. It's really possible that there can be other ways to obtain the same, to demonstrate the weak gravity conjecture. And so the takeaway is that if you want positivity plus some other ultraviolet information can be useful to demonstrate the weak gravity conjecture. So, and let me also advertise Gregory's talk on September, yes, the next one in the series, where he's going to talk about the same kind of philosophy with a different kind of UV information, but the approach is along this direction. And so this is the outline of the talk. Okay. So I will briefly review the weak gravity conjecture in its axionic version. So it's called axionic weak gravity conjecture. I will point out what's the question we addressed in our work. I will illustrate the setup which we use to address this question, and I will explain how positivity is useful in showing demonstrating the validity of the axionic weak gravity conjecture, and I will tell you how the symmetry, the SL2R symmetry, works towards demonstrating how it is useful to demonstrate the weak gravity conjecture. And briefly, I will conclude. So the weak gravity conjecture and its axionic version. So the standard formulation of the weak gravity conjecture given by the formal paper by Arcanian, Medmold, Nicholas, and Baffa in 2006 states that any effective theory where with a gauge group U1 coupled to gravity is quantum gravity consistent only if its spectrum admits at least a state whose charge to mass ratio is greater or equal than the charge to mass ratio of an extreme of black hole. And in this unit, okay, specifically in 4D, it takes this this form, and in 4D, everything here is normalized such that the charge to mass ratio of an external black hole is 1. So how does this come about? It's motivated by requiring instability and decay of external black holes, which otherwise would give some issue at low energy in the deep infrared when this steady state had to be integrated out. And so this is a Zwonthan criterion, so it's trivially satisfied when you decouple gravity, and automatically encapsulates the no global symmetries in quantum gravity statement, which is never satisfied when you switch off the gauge coupling G. And it can be generalized in 2 ways. So to multiple C1s, you can get other conditions such as the convex eye condition, and can be further used to demonstrate different version of the weak gravity conjecture called the tower or sub-lattice weak gravity conjecture. But it can also be generalized to other dimension and more generically to other p-forms potential. And in particular, the axionic weak gravity conjecture is the generalization with p equals 0 potential, which is the axion. So here we work in 4D, so everything I'm going to say is normalized with specific taking specific conventions. So the parallel works, the analogy and parallel, if you want, works as follow. So the standard photon, one form photon, gets replaced by the axion, sorry, or in its dual formulation by, sorry, by the wait, I have a problem with this. Okay, nice. Or it's in dual formulation by two form. So in this theory, we have as charge states. In the original Weak gravity conjecture, we have particles and black holes, and in the axionic version, we have instantons and gravitational instantons. The gauge coupling G is formally played by the inverse of the action decay constant, and relevant quantities, which were mass and charge, gets replaced by the axion, the on-shell value of the action, and the charge, which is actually, sorry, here is Q should be N because it's quantized, so it's discrete. So what's the weak gravity conjecture bound translated to? So now, so before it was, it needed to exist a state such that the charge to mass ratio is bigger than 1, or the mass to charge ratio is smaller than 1, and where 1 is the mass charge ratio of the extremal objects, which are extremal black holes. And in the axionic case, this statement gets replaced by requiring the existence of a state with action to charge ratio smaller than 1, or better say, than order 1 coefficient, which is set by the action to charge ratio of those extremal objects in this axionic version, which we take to be, and there is a lot of discussion about this, which we take to be regular Euclidean wormholes. So the axionic, I have to make this point clear. I want to stress that the axionic version of the weak gravity conjecture is still not very much understood. So what we take as a reference point, so what we take as the analogous to the extremal black holes in this formulation are regular Euclidean wormholes. Also because there are other kind of gravitational instantons, and these are not regular solution. So when you compute the on-shell action, you actually have to integrate, and some part of this region of integration exceeds the validity of the effective theory you're dealing with. So actually computing the on-shell effective action is not always correct within the regime of the effective theory. So the interpretation is that as extreme black holes have to decay in one sense, now if you want, the interpretation that the tunneling processes via collections of instantons with smaller action is favored over like the tunneling process of a single instanton with the same total charge of the collection. So our work stems from an observation which is valid in the context of the usual weak gravity conjecture, that higher order string corrections modify the classical black hole extremality bound, in a way that the same extreme black hole now with charge Q and M can be the weak gravity conjecture state satisfying the weak gravity conjecture. So while classically their mass to charge ratio is equal to 1, when you add higher order correction, and specifically higher order correction computed from string multiplication, and this is important, this delta M is negative. So when you compute the corrected mass to charge ratio, this is satisfied. This is more than 1, so it satisfies the weak gravity conjecture. So the question is, by the way, and this is valid only when within the effective field theory. So in particular, for macroscopic objects, which have a mass much bigger than the Planck scale, and where the semi-classical reasoning can be applied. So the question we ask is, can the same happen for Euclidean wormholes? So so again, this is like the same kind of plot we have seen before, where we are interested in understanding whether the axion to charge ratio gets corrected by higher order contribution operators in a way that now the corrected version is satisfying the axionic version of the weak gravity conjecture. So this is tantamount to ask in which case delta S is negative, basically. So this is our main goal, to understand on which circumstances we can prove that delta S is negative. So briefly, so the setup we take is the following. So we take an axion-dilaton-gravity theory, and we add 4 higher order correction in the form of 4 derivative corrections. So the classical system is the following. So we have the Einstein-Hilbert term, the dilaton kinetic, and the axion kinetic terms. And when beta, in particular, when beta is equal to 0, beta here parameterizes the axion to dilaton coupling. So we end up with an axion gravity system where basically the dilaton formally has been integrated out. So you can think about this dilaton to be supermassive, and you integrate out, and you end up with an axion gravity system. Solution to this classical solution to this system are the Euclidean wormholes. These are the regular ones, and they are valid, and they are regular and smooth for specific values of beta. So you cannot have such solution for any beta, but only for betas more than 4/√6. And this is the picture. This is like the full wormhole, which can be interpreted as an instanton pair. And so the wormhole is asymptotically flat on both sides, and it has a so-called wormhole neck at a specific value of R, and which is also the smaller like value of R possible. And so this is the geometry. And again, I don't have a point. And when you go and compute the action, and now we're interested in the instanton action, so in the semi-wormhole action. The action takes this form, and so you can see when you send beta to 0, you obtain the action value for axion gravity system, and this value of the action is what sets formally the order 1 coefficient in the weak gravity conjecture statement. So now what we want to do is adding higher order correction in the form of 4 derivative corrections. So the most generic correction you can add is this form. So there's the phi fourth, the theta fourth, and then combination of the phi square and the theta square. And then there's also a contribution given by the Weil tensor and the gravitational Chern-Simons. And but in our case, the last 2 contributions given by the Weil tensor and the gravitational Chern-Simons is going to be trivially vanishing, because our solutions are conformally, they can be put in a conformal gauge, so they're going to be 0. So when you evaluate this correction, you get the following. So in case there is no dilaton, so when beta is equal to 0, in the axion gravity system, the action correction is given just by basically minus A2, the coefficient A2. And when instead the dilaton is turned on and is present, it's way more complicated, and you cannot really put this in a this is like actually the nicer way you can recast your action. So you can see that in this case, so yes, sorry, let me say that positivity, so this is important, positivity condition determine the following behavior for the coefficients of our higher order derivative terms. And specifically, you can immediately see that since A2 is positive, then in the axion gravity system, the delta S is negative. So this automatically means that positivity implies the weak gravity conjecture in this case. But in the more complicated setup, when a dilaton is dynamical and massless, so you can see that there is actually, so this is like the picture. So you cannot tell whether the delta S is negative, positive, or zero. It can be anything basically, because here you have, if you check, you can have a really big A4, which is really big and positive A4, which is consistent with the positivity condition. And if it's much bigger than anything else, for example, this delta S can be positive. And this is like summarized and in this sketch down here, which is actually a simplified illustration in the oh sorry, this is like A, not alpha, it's like A coefficients, A1 equal A2 plane. So the allowed region, sorry, the forbidden region by positivity is the gray one. So the allowed region, which satisfies the positivity for the coefficient A3 and A4, is this region, which is the white and the pink region. But specifically, the pink region is the region where you can compute delta S to be positive. So this is the region, this is really relevant. This is a region where positivity is satisfied, but the weak gravity conjecture is violated. And yes, and this region is a model dependent region because it really depends on the specific form of this coefficient, which depends on phi. So before telling you how to fix this, how to include any like UV ingredient in order to prove the weak gravity conjecture in this case, let me just tell you how positivity works quickly. So take the simplest axion gravity effectivity theory, and in this case, for example, the coefficient alpha can arise after integrating out, as I said, a massive scalar. So in this case, the dilaton, for example. And in so doing, you know that you have the dilaton coupling to the axion. So you get this Feynman diagram, and when you go to the infrared low energies, you create this 4-point axion vertex, and you can compute and you can show that alpha there must be positive, and the sign of alpha is related to the sign of the propagator by unitarity, basically. But more generically, you can show, and this has been done by these folks, Adams, Arkanimed, Boschi, Mikolis, and Ratazzi in 2006, that generically the positivity of this coefficient follows from unitarity, analyticity, and locality of ultraviolet scattering amplitudes. And this works actually under the assumption that some gravitational Regge states are, so in this case, the string oscillation, are subdominant when you compute this UV scattering amplitudes. And this point has been explained in the work by Yuta, Toshifumi, and Gary 2 years ago. Oh, okay. What happened? There's one slide missing. Why? Okay. So, okay, now we can go back to the axion-dilaton-gravity system, and we ask, can we assume some other additional property and show that helps showing that the weak gravity conjecture, the axion weak gravity conjecture is satisfied. So we take SL2R symmetry and we impose SL2R symmetry on our effective theory. And the motivation is basically we are just extending the symmetry. This is a symmetry of the two derivative action to the higher order terms. So the two derivative action has this symmetry once you recast the axion and the dilaton with the axion-dilaton tau. And you extend this to higher order for derivative terms. And if you do so, you immediately realize that you actually have just two possibilities to write SL2R invariant operators, and which are these ones, where where we identified their higher order coefficients, their coefficients as lambda 1 and lambda 2, which are constants. So you have that basically the four-dimensional parameter space goes to a two-dimensional parameter space, where lambda 1 and lambda 2 now will be related to some combination of A1, A2, A3, and A4. So basically what we are doing, we're technically adding structure to our effective theory. So what happens? So when you evaluate delta S, now it can be put in a really simple form, which is just this one, which is basically again minus lambda 1 plus lambda 2. And now positivity, you can show that implies lambda 1 plus lambda 2 non-negative, and positive and non-negative also lambda 2. And immediately, so also in this case, we have that the axionic version of the weak gravity conjecture is satisfied. So coming back to our plot, this is what it means. So SR2 symmetries, you can see in the corner here down, implies that alpha 1 is equal to alpha 2, and this can be related to lambda 1, lambda 2, and also that A3PA plus A4 is equal to twice A1. So basically, it's like the blue line, which shows you that we are in the white region, which satisfied where both positivity and the weak gravity conjecture are satisfied. But again, you can understand that this white region, I mean, it's pretty big, and so there may be other UV ingredients such that you end up in this white region. So SL2R is just one, and is sufficient to imply the weak gravity, but there may be others. And concluding, this is like a summary and an outlook. So we provided some evidence for the axionic version of the weak gravity conjecture, which is really relevant for phenome model building, particular inflation. And how did we do it? We did it by studying the relationship of the axionic weak gravity conjecture against positivity in axion-dilaton-gravity system with a specific caveat on these Regge states. And we found that in absence of dilaton, positivity is enough to imply the axionic version of the weak gravity. But when we turn off a dilaton, massless dilaton, positivity is not enough. And yes, there is a region in effective field theory parameter space where the weak gravity conjecture is violated even if positivity is satisfied. And so this, to some extent, is really interesting because it provides a possibility for counterexamples. So if you take a theory, for example, you compactify and you find that the coefficient they satisfy positivity, you expect generically they satisfy positivity, but they put the effective theory in the parameter space such that the weak gravity conjecture is violated, then it's really interesting to see why it happens to be the case. So we enriched, but if we enrich the effective theory structure with SL2R symmetry, we can prove that this is sufficient to show, again, to demonstrate the axionic version of the weak gravity. And so the question now is, are there any other relevant or equally relevant ultraviolet inputs that are useful to demonstrate the weak gravity conjecture? And yeah, you can, and Gregory is going to tell you something about this in a month. And I find interesting to keep working on this direction, because in this way we can find the ultraviolet properties that are either necessary or sufficient. In this case, we found a sufficient one for the weak gravity conjecture, and maybe we can apply the same kind of reasoning to others wanton conjectures. And in so doing, the hope is to find what really makes string theory tick. So its relevant features as a theory of quantum gravity. So that's all basically. Thank you.
All right, thank you for the very nice talk, Stefano. We can use our clap emojis. Are there any questions? All right, Ben has a question first.
Yep.
Hi, Stefano. Thanks for the nice talk.
Yep.
My question was, what's the motivation for assuming some SL2R symmetry of the four derivative operators? I know that you could have such a thing in the two derivative order, but I wouldn't expect it to be there at the four derivative order.
Yeah. So there's no not strong motivation. So our point is like it's motivated by, if you want, it has a duality flavor. So in type 2b it's well motivated. We expect this duality to work, and but this is not the case, for example, for heterotic. But in heterotic you have ODD, for example. So you can run the same kind of argument also with other kind of ultraviolet ingredients, and I think Gregory is going to talk about ODD as well in his talk. So if you want, our point is basically trying to to figure out what's a possible property that satisfied is helpful in satisfying the weak gravity. And yeah, but I think more research is needed in these directions to really understand which one are really the relevant property to for quantum gravity. And so yeah, if you want, the naive answer to your question is yes, duality in string theory, but it's not always the case. Yes.
Okay, but duality would be SL2Z probably, right? Not SL2R.
Yeah. Well, yeah. Actually, we work with LS2Z because it automatically implies SL2R because of the shift symmetry of the action. But in our paper is LS2Z. So yeah, it's LS2Z. I should have written SL2Z, but SL2R is just upgraded with, because we have a shift symmetry of the action. Yes, the axion. Yeah.
Okay, thank you.
No problem.
Okay, our next question is from Jose.
Hello, thanks for the nice talk.
Yeah, hi,
would you expect that in some regime, higher order corrections could be relevant, or that only the fixed derivatives then could be just the thing you need?
So sorry, can you repeat the question?
If you would expect that that other higher derivative operators could be relevant in some regime, or sticking to the first corrections should be enough?
Okay. We are working perturbatively. Sorry, I should have said this. So our work is perturbatively, and we are also focusing on the first order, and in the alpha prime expansion, if you want. So these are the most relevant to our to our under our assumptions, and but yeah, I wouldn't really, because actually, so whenever you compute higher order terms, let me see, if I can show you. Where is it? Here, where is it? Here. Yeah, you can see it maybe from here. So here, this is just a constant. So delta S is constant when you take the first order. But when you go on, next order gonna be order 1 over the charge. And since we are working like in semi-classical limit where the charge is big, then these are subdominant respect to this order ones. So this is like the reason why. It depends on the regime. So we assume to work in the semi-classical approximation where the charge is big.
I see. Thanks. Thanks.
No.
Okay, if there are no further questions, let's thank Stefano again. And thank you for both of the speakers today for your excellent talks.